gravitational field as having a kind of well-defined magnitude, right? So there are things that are not electrically charged, and you can have a zero electromagnetic field, or in quantum mechanics, a sort of quasi-vacuum statistically. But there's never anything that's sort of not gravitationally charged. And there's never not a gravitational field. At least you can't tell if there's a gravitational field. You can say, well, it's sort of net zero locally because it feels like we're freely floating, but we could be freely falling. So in spite of that, however, Einstein was still trying to combine two things. One is this idea I talked about last time, the identity of gravity with space-time geometry. But he was also thinking that gravity, it should be a field like the electromagnetic field, even though it has these important differences. And therefore, it should be more like Maxwell's field than like Newton's. So if you think about what was Newton's gravitational field, and we talked about it a bit, I mean, you could say that Newton was the first one to have the idea of a field, but only in a kind of funny sense of the word field. So if you imagine a mass, Newton said, thanks to the theory of universal gravitation, or the fact of universal gravitation, you can pick any point and say any point in the region surrounding any body and say what the gravitational field is there, or would be there. Now you don't have to think about it that way. You could say, well, it's a relationship between two bodies directly. But Newton, like everybody else in his time, wasn't really happy about the idea of action and distance. He didn't see any way of thinking of gravity coherently as involving a vortex or particles moving back and forth. But he still thought, he refers to it at one point in Kippy as a power diffused through the space around the body. So it's kind of like, well, one philosopher got in the habit of calling it, and got other people in the habit of calling it an acceleration field. Because it just means wherever you are at any point surrounding this mass, there's the value of the acceleration that a body right there would feel. And the fact that the acceleration belongs to the field, so to speak, is an expression of that fact that I was referring to. I don't think I used this expression, although I've been talking about it for a long time. The equivalence principle. This is a name that Einstein came up with for the fact that I've been talking about for the past several lectures, namely the equivalence of gravity and inertia, the equivalence of gravitational and inertial mass. So when you consider this example that I talked about of the box in a static gravitational field, right? And you're feeling your weight toward the floor, and the weight of an object you're trying to hold up, and the gravitational downward acceleration, and that's equivalent to thinking of the box as moving upward and thinking you're feeling the inertial resistance of the body instead of its weight. Because the gravitational attraction is always proportional to the weight. Right? Or sorry, the gravitational attraction is the weight. The gravitational weight is always proportional to the mass because it's the mass times the same acceleration, no matter what mass it is. So there's various consequences of this, right? One is, well, no matter what weight you put here, right, the gravitational acceleration will be the acceleration times that mass, right? The weight will be the acceleration times that mass, whatever it might be. So this is it's a sort of universal generalization of Galileo's principle that any two bodies feel the same acceleration and the same gravitational field. Right? Except that Galileo thought he only knew that it holds for small bodies near the Earth, and Newton extended it to any bodies anywhere, at least theoretically. Another consequence of that is that you can compute from Newton's gravitation theory. It's something that he certainly knew, and that even his opponents thought was really impressive at the time. Once you understand the universality of gravity, then you can think, well, the weight is the gravitational acceleration times the mass. Therefore, if you were on the moon, you can guess how your weight would be different. Right? You can actually calculate from Newton's theory how much you would weigh on Jupiter and all these, because it's the same mass times the different acceleration that Jupiter's mass causes. Anyway, that's a field in a sort of primitive sense. Because wherever you are in space, Newton's theory tells you this is the acceleration you would feel independently of your mass. Now the Maxwell, let me say one more thing about this, right? So that is, thanks to Newton's formula, right, the gravitational force is equal to the gravitational constant, right, times the product of the masses over the distance. That means that a sudden, if you could imagine what happening, a sudden change in the distribution of masses would imply a universal sudden change in the gravitational field. Right? Equally sudden, instantaneous, because there's no time in this equation, right? The equation might be wrong, maybe gravity does sort of propagate in time, but the equation, Newton's theory doesn't say anything about that. Einstein's theory is based on the idea that the gravitational field is more like the Maxwell field, and that the electromagnetic field is very different. If you disturb an electromagnetic source, when you create light waves, for example, or you just change the distribution of electromagnetically charged bodies, right, then there's a disturbance that propagates at the speed of light through the field. So the whole idea of the ether was based on this notion that, when there's an electromagnetic disturbance, it moves through space. And this is what's in the modern idea of the field that was never in Newton's idea of the gravitational field. And this is why people are reluctant to really admit that Newton's theory is like a field theory, because it doesn't have any dynamics, whereas Maxwell's whole idea, incidentally, which was inspired by Faraday, was precisely that in order to understand electric charge, magnetic attraction, and light propagation, and all these things that are electromagnetic in nature, you have to understand something dynamical happening in the space between the charged bodies. And that his theory of the electromagnetic field is the theory of the dynamical states of the ether. Now Einstein's theory, of course, as we saw, you can just sort of chuck the idea of the ether and take the electromagnetic field as basic, but it's still a dynamical structure in between two charged bodies, such that if you were to change one of them, there's a sort of an event that happens, right, that propagates from one to the other. And so there is something going on in the space between charged bodies that's happening at a finite speed, and it's happening at the speed of light. So Einstein's gravitation theory is like Newton's in a lot of respects that we've already talked about, but it makes the Newtonian idea into more like a classical dynamical field idea in just this sense that gravity too is going to propagate through space at the speed of light. Gravitational changes would propagate through space at the speed of light. So it's a consequence of this theory that whenever there are sort of gravitational events, and they're happening all the time, there should be waves propagating through space-time. And in a sense, you could say that's one of those things about Einstein's theory one of the reasons I mentioned this lecture that I did last spring, in case you want to watch it on YouTube, is that I was trying to identify one of the things about Einstein's theory that you could say he taught us about the universe that are just true, even if in the next evolution of physics we throw away his basic picture of the relationship between gravity and space-time geometry. And this is probably one of them. Well, I would have said this is one of them 2 weeks ago. I think I would more strongly affirm this now that there's actual direct evidence of gravitational waves. That gravity is that kind of dynamical field. In a sense, there was always indirect evidence of it. Not always, but for a while, there's been indirect evidence of it. So, Newton's theory says that when you have a gravitationally isolated system, more or less, like bodies revolving around their center of gravity, unless there's some kind of inertial disturbance, right? A medium that's slowing them down or something. These motions can persist for a long time. That's how he put it. That somehow, this is one of his arguments against the existence of a material medium that keeps the planets moving. He argued, well, the planets and comets move so freely, and they slow down so little, in fact, less than is detectable over time that we can sort of measure them. That you can put an upper bound on the density of any medium that there might be out there. If there is a medium, it's got to be so rare, a material medium, that is to say massive particles like dust or something, clouds of dust that we can't see. It has to be so rare that it's not slowing the planets or the comets down at all. At least not over human history. So, but in any case, there's no reason if you have, say, two objects that are kind of orbiting their common center of gravity because they're sort of trapped to one another. There's no reason for that system to change over time unless there's something interfering with it. Now, Einstein's theory says that if you have a system like this, in principle, it should actually lose energy to radiation. If it's like a dynamical field, like the electromagnetic field, it should sort of radiate away. There should always be gravitational waves emanating from it. It should be losing energy to radiation, gravitational radiation. And that's something that would be true if Einstein's theory is sort of empirically right. And that's something that the next theory of gravity is going to have to somehow incorporate. So you say this system, if it's Newtonian, well, it could go on like this forever. But if it's Einsteinian, it's very subtly losing energy. And there are empirical tests of this. Like, for example, a binary pulsar. A couple of neutron stars that are trapped in each other's orbits and emitting a sort of pulse that depends on the sort of occultation of radiation coming from them. And you can sort of check that Einstein's theory applies to this highly massive system that's so massive that you can notice the differences between it and Newton's theory, the different predictions that are made. Because most of the time, Einstein's theory makes predictions so close to Newton's theory that you can't measure the difference. But in these very massive systems, you can. So you could say, well, indirectly, that confirms Einstein's theory of gravitational radiation because it's losing energy in the way that you would expect it to. On the other hand, a really cataclysmic event should actually produce detectable waves. And that would be a direct confirmation of the theory, not something we haven't seen until now. But because it's a sort of necessary consequence of Einstein's theory, then it's something that absolutely should be observed. Now, of course, to be cataclysmic enough, it has to involve very large masses. I forget the exact figures of like the two black holes that are collapsed into one another. 30 and 35 solar masses. I'll come back to the idea of a black hole. I haven't really talked about that. I think some people ask me about that last week. Isn't that right? But this is a kind of cataclysmic event. When you have these things falling toward one another, more rapidly revolving around their center of mass, and eventually collapsing into one another, you actually, it's creating a disturbance in the gravitational field that propagates like a wave at the speed of light. And then, of course, when they actually do sort of collapse into one another, that's an even more cataclysmic event. So that's something you should be able to detect. That's why they built these detectors in the first place. The LIGO, what is that? Long, I think they crammed a lot of words in the L. Because it doesn't sound like anything. Because it's like long baseline interferometry, gravitational observatory. So I guess if you hyphenate long baseline, it works out okay. So you have laser beams in an array in two different places. I think there's three of these, but the third one isn't really online. Because what I read, it was really a freak stroke of luck, because they were sort of down for maintenance until recently, very recently, and then they were sort of got back online just in time for this observation. You have laser beams going back and forth, something like a Michelson-Morley interferometer. And very small changes in these arrays of laser beams, which are very large. I forget how large they are, but they're large. Would, in principle, show that the straight, if you want to put it in geometrical terms, the straight lines in which these light beams are traveling are affected by a ripple in the space-time geometry. And of course, you have to have two of them at very different locations, just so that you can be sure that it's very improbable that some freak disturbance over here would also happen at the very same time over here. I forget where they are now, but they're pretty far apart. But I think there's another one in Europe that's not working yet. Or I can't remember. So this is the first time there's ever been direct evidence for gravitational radiation, the actual detection of the waves. There's this indirect evidence that existed before of events that are compatible with Einstein's theory, but not the actual detection of a wave. And that's a really remarkable thing. I mean, that's there's a long history of null experiments going on to test the basis of Einstein's theory, the equivalence principle in particular. But this is the first sort of, well, this is I think it's fair to say, this is a radically new prediction. So, for example, when, in 1919, when there was that solar eclipse observation that supposedly proved Einstein's theory and disproved Newton's. Well, when I say supposedly, I mean wasn't an extremely accurate experiment. Basically, what does it show? It shows that starlight coming from some star is visible on the Earth even though it shouldn't be. It should be occulted by the sun. So the apparent position of the star is here. I mean, this is greatly exaggerated, of course. But the actual star is over here, which means that the light from the star is bent as it passes the sun. So you're actually seeing it as if it were over here somewhere. Now, so the questionable thing about this is, what do they mean Newton's theory? What does Newton's theory say about light bending? I think I mentioned this before. Newton wouldn't have known what to say about the relation between light and gravity, except to sort of speculate. Well, if it's a small, massive particle, and of course it would be affected by gravity, but it's moving really fast, so we would never be able to detect, light bending. So when Einstein's theory made a sort of, when Einstein realized that from his theory he could get a kind of detectable prediction for light bending near a mass the size of the sun, what you could do is ask, well, suppose Newton's theory did make a prediction about it. Right? Suppose it was a tiny, massive particle and it was being scattered by the sun. What would happen? So in other words, the prediction of light bending isn't a radical new thing that you couldn't think of until you thought of general relativity. It's something you could think of with Newton's theory too. Depending on how you view the relationship between gravity and light. Is it massive? Is it affected by gravity or not? But of course in Newton's theory, it isn't being affected by gravity unless it's massive, because gravity makes masses move toward one another. Now, Einstein's theory, we saw just from special relativity, right? Einstein's theory treats light as a massless particle that travels on these special null trajectories of space-time, right? The trajectories of zero length. So any massive particle travels on a finite path through space-time, right? Non-zero space-time length. And only a massless particle, or gravitational radiation, which is also massless, would travel on a null trajectory. So the only way for light in Einstein's theory to be affected by the sun is if the space-time itself is curved. Because light doesn't have a mass, there's no reason for it to fall in a gravitational field if gravity is an attraction between two masses. Do you see what I mean by that? So because light's a massive particle light is a massless particle according to special relativity. Well, special relativity doesn't say anything about whether it's a particle or a wave, right? You could just say, in 1905, Einstein already had the idea of light quanta, which we'll talk about after the break. But in developing general relativity, it's not really relevant. Right? Quantum considerations are not relevant to special and general relativity as he was thinking about them at the time. And they're two separate problems. But light is a massless particle, so if your theory of gravitation is that it's an attraction between massive objects, then there's no reason for light to be attracted. So this is what's really remarkably new about the prediction of light bending. That you've got a massless particle, and its trajectory in the presence of a large mass is altered. Well, it's a radically new thing to say that the bending of light rays is a curvature of the space-time geometry. Because it's a massless particle, and there isn't any particular reason for it to be, for it to be affected by the gravitational field. It's just that Newton's theory doesn't tell you one way or the other what you should think about light. Now, for the same reason, the idea of a black hole is a really old idea. Somebody asked me about this after class, I think. The idea of a black hole goes back to the 18th century. Because if you think of light as a very small particle that is affected by gravity, but just not noticeably, then it's a very simple problem in retrospect. Of course, the people who thought it were great geniuses, Laplace and an English person whose name I can't remember. I think Laplace was more public about it. But, so it's a very simple problem, though, in retrospect. Because if you think light is just a particle, it's just moving really fast, right? So even back then, they knew roughly how fast it goes, right? And they could understand, even though it wasn't relevant at the time, what we would call the concept of escape velocity. Right, so you go up in an airplane, you're going nowhere near any kind of escape velocity, right? You're always just, the velocity of an airplane with a space shuttle is always really small compared to the velocity it would take to actually escape from the Earth's gravity. On the other hand, if you want to go to the moon, right, you have to somehow get out of the Earth's gravitational field. What does escape velocity mean? Well, it's a very simple idea, right? You're going around this sphere in an orbit, right? If you're in this orbit, right, and you're stably staying in this orbit in the space shuttle, right? Basically, that means that the amount of acceleration downward you're experiencing and the amount of, so to speak, horizontal motion parallel, motion not getting any closer to or further from the Earth, are exactly balanced, right? If you were sort of going fast enough to sort of recede from this orbit along the tangent, then you could get to a higher orbit, right? So you can stay in the orbit you're in if you just exactly balance the two things, right? How fast you're going forward and how fast you're accelerating down. On the other hand, if you slow down, then the acceleration downward is going to be overcoming how far you're moving forward. And so either you can move to a lower but stable orbit, or you can, and Newton certainly understood this because he has pictures of it in his book, right? You just sort of spiral into the Earth, right? So you slowed the moon down, for example, it would spiral into the Earth. Because it's not going, it wouldn't be going fast enough to stay in that orbit anymore. On the other hand, if you speeded it up, it could go to a higher orbit, and if you really speeded it up, it could go somewhere else. Right? So the whole idea of light bending, or it's like any other kind of bending, right? If you could imagine, not light, but say a massive particle of some kind, like say a comet. Comets do kind of what, in a Newtonian point of view, you would think of as the same thing as light bending, right? Comets come really close to the sun, and then they just kind of go off. Now, of course, we know all these periodic comets that eventually are going to come back, but they wouldn't have to, right? If their velocity was great enough that they just sort of passed through our solar system and left, right? That can happen. It's all a question of whether your velocity is great enough, right? The velocity of the comets, these comets we know, like Halley's Comet, over a long period. Well, it slows down enough when it gets further away from the Earth in 75 years or something, no, half of that, right? 79 years. So you guys could see it again. Well, you missed it last time, but you could see it. I think it was the 80s that was here.
I was aware. So.
But you probably were a child.
Really appreciate it.
It made you cry, probably.
Everything made me cry that age.
I guess I look older than I am, because I was once asked by someone interviewing me about American politics and how I felt about the Kennedy assassination. Yeah, I cried. That's about what I was doing pretty much any time of day at that period. Anyway, eventually it just has lost enough velocity that the sun's gravity can begin pulling it back. Right, so it's just a question of, how fast are you going compared to the gravitational field you're trying to escape from, right? So light's going very fast. Too fast to be captured by the sun, but not fast enough to completely escape having its path altered by the sun as it passes by. So it's a simple Newtonian calculation. Well, how big of a mass would you have to have in an area confined to the size of the sun, say, in order for light going past the sun to get trapped? Or you could think of it this way. I mean, if the sun's always producing light through nuclear fusion, right? But when it escapes from the sun, is it going fast enough to escape from the sun's gravity? Because it has to be going fast enough. Well, light is always traveling at 300,000 kilometers per second. Well, is that fast enough to escape? That all depends on how big the mass is. And that's the basic idea of a black hole, and that's why Laplace thought of it a long time ago. Just said, well, you could imagine a star that was so massive that light, assuming that light does get affected by gravity, light is not moving fast enough to escape from its gravitational pull. So, the Newtonian ideas of light bending are all based on this idea of just accepting the hypothesis that light is a gravitationally affected particle. And if you look at that in space-time, you can just say, here's the world tube of your massive object, your collapsing star, right? Now, in Newtonian terms, you could just say, well, how fast do I have to be going, right? Suppose here's a photon that's escaping from the sun at the velocity of light, that it's being pulled back by gravity to such an extent that it actually never gets away. Now, if you think about it in special relativity now, then you have to think of the light cone, right? So suppose you're really far away from this mass. Here's the light cone, right? And you might say, if I'm here, I'm so far away from that massive thing that light appears to go the same speed in all directions, right? The cone would look symmetrical. On the other hand, you could imagine that if you're close enough to the sun, the light cones are sort of distorted, and the space-time structure is warped by the presence of this enormous mass. That means the light cones are sort of, as you get closer, they're sort of bent toward the planet, or not the planet, but the enormous collapsing star. And there's going to be a certain point, right, where traveling at the speed of light in the opposite direction, you simply can't get any further away from the sun, or the mass, whatever it is. So you could imagine if this is your trajectory, right? You started from here in some region that's really far away from that mass, right? But because it is such a huge mass, you are gradually falling into it. Well, its black holeness, so to speak, is expressed by the fact that as you get closer, right, your light cone is sort of being distorted in such a way that it's bent towards the, and you could imagine, you start sending out signals, right, from points along your own trajectory, right? Now, the parts of the universe you can reach by a signal are being more and more severely restricted by the fact that you're approaching this black hole, right? Eventually, there'll be this point where your very last signal can sort of escape to the outside world, and then there'll be a point where the light cone on your trajectory, let's say this is the light cone on your trajectory, right? Looks like this, and that means even a signal you send at the speed of light is never going to get any further away from the mass. So anyone who's further away from that mass than you are is not going to receive the signal anymore. That was your last message to the outside world. This is called the horizon of the black hole. You can't see over it, so to speak. It's like the regular horizon. Except the regular horizon is spatial. This is a space-time horizon because it's the light cone of space-time that's been distorted in such a way that you simply can't get a signal anymore outside of it. And then, of course, as you get closer and closer to it, right, your light signals too are going to be just falling into the central mass. So that's the Einstein idea of a light cone. So the black hole itself isn't a radically new prediction. It's that it's the relationship between light and gravity that's radically new in Einstein's theory. And then, of course, this other thing that isn't really in, well, it's just not part of Newton's theory at all. The gravitation propagates like a wave. And therefore has a dynamical structure like the electromagnetic field, even though it has this fundamental difference from the electromagnetic field of the equivalence principle, right? The electromagnetic field differentiates between charged and uncharged bodies, whereas the gravitational field has the same effect on everything. So in a sense, that's what really establishes how strange this theory of space-time is. That not just that it has a non-Euclidean geometry, but that it has a dynamical geometry. In a way, though, it's inevitable, right? If you start from the idea, well, the path of a freely falling body is a geodesic of space-time, well, then you have to accept the fact that the geodesics of space-time do not behave like the geodesics of Euclidean space. Right? They behave like the straight lines of a curved space. Therefore, the only way you can make sense of the relative behavior of falling bodies is by thinking that they're geodesics not of a Euclidean space-time, but of a non-Euclidean space-time, because they have all these behaviors we talked about last time of converging on one another. And you can measure the curvature of space-time by measuring what in physics is called the geodesic deviation, right? So if you take geodesic lines on a flat plane, I mentioned this before, right? They approach one another at a constant rate, and they separate from one another at a constant rate. But on a curved space-time, they like geodesics on a sphere, like lines of longitude, they approach one another at a non-uniform rate, and then they recede from one another at a non-uniform rate. Was a basic feature of a flat space or a flat space-time. You don't have geodesic deviation. Geodesics that are parallel stay parallel. But in a non-flat space, they accelerate toward one another, and that geodesic deviation is another way of thinking of measuring the curvature of space-time. There are different ways you can think about it. If you think back to what we were talking about earlier in the course with Poincaré, right? What are different ways of thinking about the measure of curvature? That's one of them. Another one you can think of is the failure of parallel transport. Did I mention this? So if you think of this as an arrow, in other words, it has a direction, an orientation, lying on the plane of the blackboard, right? You can move it anywhere you like on the blackboard and keep it in the same orientation. You can move it in straight lines. Of course, if you turn it, that will change its orientation. But you can move it along the surface in straight lines without changing its orientation. Now, if you think of the same arrow on the surface of the sphere, well, it's obvious that there are some paths you could take around the sphere that would leave it, that you bring it back to the same orientation. But some paths where it wouldn't, right? So if you move it, say, from the North Pole, following the line of longitude, all the way down to the equator, then move it along the equator, all the way around to the opposite side, to a line of longitude 180 degrees away, then move it back, you can just reverse its orientation. Right? Well, that's called a failure of parallel transport. So, of course, if you just send it around like this, that's a parallel transport. So, the conclusion that you can draw is that in a curved space, parallel transport is path dependent. Right? On the blackboard, I can just move it anywhere I like and always keep it in the same orientation following the contours of the blackboard. Right? On a curved surface, I simply can't do that. On every path, it depends on the path I take. So, all of these are ways of thinking. You can use the paths of falling particles as sort of probes of the curvature of space-time. But it's very much like a completion of this idea that Poincaré had. If you have stipulated that light always travels in a straight line, then you can treat light rays as probing the geometry of space. On the other hand, Poincaré thought, well, you're free to choose. If you don't like non-Euclidean geometry, then just stipulate that geometry is Euclidean, and then, introduce a force to explain why light isn't traveling in a straight line, or whatever you feel you have to do. It's totally up to you. Now, Einstein's philosophical attitude is a little bit different from that, because he isn't saying, well, look, this peculiar feature that falling bodies behave like inertially moving bodies enables you to adopt this convention if you like. What he's saying is, well, this peculiar fact about gravity sort of compels you to regard this as the only really reasonable definition of a space-time geodesic. This isn't how he put it. This is kind of a reconstruction of one of his ways of arguing. But it's kind of like what he said about simultaneity. Well, if you want a reasonable definition of simultaneity, I've got one, and I really don't know where you're going to get a different one. Right? So it's not like you have a complete freedom to stipulate what you like. So Einstein's argument is, once again, like the argument he gave before, that's kind of conceptual and epistemological, saying, well, there's every reason to treat the passive falling bodies as the geodesics of space-time. Therefore, it's not really a matter of stipulation. It's a way of expressing this really peculiar fact about gravity. That it has this peculiar relationship to inertia. And that if we made a stipulation that space-time is flat, and that gravitational trajectories therefore are not geodesics, we would be making a kind of, that would be an arbitrary choice that was ignoring something we've discovered about gravity, this peculiar relationship between gravity and inertia. Let's not ignore it. Let the theory express that peculiar fact about the universe. Just as in special relativity, we want the theory to express this invariance of the velocity of light and not try to make excuses for it. And as a result of that, you're then in a position to say, well, when I fling particles out in the gravitational field and watch how their trajectories accelerate with respect to one another, I'm measuring the curvature of space-time. Right? When I see how a massless particle, like a light particle, bends in the vicinity of an enormous mass, I'm probing the effect that that mass is having on the geodesics of space-time. But then, of course, there is this great, it's the other half, and in some ways you could say this is the more important half, but it really doesn't matter because they're intertwined. Right? Well, you could say we've sort of made geometry, we've made gravity into something geometrical. We've geometrized gravity. Well, that's kind of just one way of looking at it. Right? The other way of looking at it is we've taken geometry and made it into something dynamical. In a way that even gravity wasn't that dynamical in Newton's theory because gravity was sort of a static field. There was no theory of how it propagates. But now gravity is a dynamical field because it has dynamics in between two gravitating sources, just like the electromagnetic field. And because we've made this identification of gravity and space-time structure, we've made space-time geometry into a dynamical structure. And if you think that was really the most interesting thing about general relativity, which I think you can't deny that's either the most interesting thing or one of the two equally most interesting things, then you have to regard this news of the detection of gravitational waves as an incredible confirmation. Anyway, that's what about that? I don't have somebody to rush out to, so if you have any questions about that. I don't know how much I can help you understand the news reports, but that's how I see them fitting into the whole context. I was going to see if we can dig up some videos on YouTube. probably have seen them all now. I like the ones on the BBC. Question? I guess you're free to go and do whatever it is you do. It's